Okay, so say we flip this switch and at time t equals 0, and we can use the loop rule here, where we have EMF of the power supply minus the voltage drop across the resistor minus the voltage drop across the inductor. And so we have this equation from the loop rule, or if you like, maybe a little safer, just basically conservation of energy. We follow a positive charge going around here. We just multiply by Q everywhere, and that would be changes in energy as we go around the loop. And what I want to do is multiply everything by I. Let's multiply each term by I. I'm going to rewrite it a little bit as well. Let's say I times E, and then let's move the negative terms to the other side. Okay. So we just moved these two terms to the other side, made those positive, and multiplied every term by I. So remember, for a power supply, the power delivered by a battery is current times voltage. And the power dissipated by a resistor is I squared R. So if we think in terms of energy, the battery, here is the rate that the battery is supplying energy. This term here is the rate that the resistor is dissipating energy, typically converting it into heat. But these two, like if we ignore this term, these two, we've got, this is some, say, non-zero term. So the battery, let's say in some time interval, the battery supplies 1,000 joules of energy. This is going to be less than 1,000. So like, where is that extra energy going? And we know that when this current is building up, we start at zero current, we flip the switch, and so current starts building up in the circuit. So the battery is supplying energy, the resistor is dissipating some, but we know that that doesn't account for everything. There's also this current building up in the inductor, and so we can identify this term as the rate that energy is building up in the inductor. I'm going to say the rate that energy is going into the inductor. So the battery is putting energy in. Some of it's going into the resistor and being converted into heat. The rest of it is going into the inductor. And we interpret that energy here as being stored in the magnetic field. So let's say, I'm going to erase most of this. Let's say UB is the potential energy stored in the magnetic field. Just to save room, I'll call it B field. So basically what we have here, the rate that energy is going into the inductor, what we have is that d UB over dt is equal to Li di dt. So it's a rate. So how quickly is energy being, building up in this inductor? That's du dt. That's equal to this term Li di dt. Okay. So does that make sense? Okay. So let's erase this now. This is kind of the result we want. And we can write this in a little shorter way. Let's get rid of the dt. dUB equals Li di. Just by like integrating by t, we can do that. And now if we integrate this, we can take the L out of the integral. So let's say we start out with, if the current is 0, there's no magnetic field, so clearly the energy stored in the magnetic field is 0. And then say let's put primes here, we go to some current I, and we end up with a certain energy in the magnetic field there. So let's integrate this. On the left side, we're just going to have UB minus 0. Or the energy in the magnetic field. And doing this integral of I di, that's just like the integral of x dx, that's 1/2 I squared. So we have L times 1/2 I squared, or the energy stored in the magnetic field is 1/2 L I squared. I really want to be consistent with currents and charges, like I always mix those up. So I'm kind of out of room here. Let's just write this down here. So that is the energy stored in a magnetic field, 1/2 Li squared. Okay. So I don't know, any questions on that? All right. Now let's consider a solenoid. Let's say this inductor here is a solenoid, and we close the switch and let it build up to its maximum current. Let's find the total energy stored in the solenoid. So we have the energy would be 1/2 Li squared. But we know the inductance of a solenoid, so let's plug that in. So L is mu naught N squared. Now remember I mentioned earlier, we had this solenoid with a length L and a cross-section area A. And notice that A times L is the volume. So let's do that. We have mu naught N squared times the volume. And we have a 1/2 in front. So 1/2, there's L, which is mu naught N squared AL, or mu naught N squared times the volume. And then times I squared. We don't have a magnetic field for a solenoid written down. The magnetic field inside a solenoid is mu naught lowercase n times I. So let's do this. Let's multiply by mu naught divided by mu naught, and hopefully you'll see why in a moment. Here we can write that as 1/2 mu naught, and then we have mu naught squared, so mu naught times mu naught on top, n squared I squared times v. And I'm going to write a lowercase u. So I'll write it very small. That's a lowercase u. That's the energy density. So we have like the energy. Remember, most of the magnetic field is inside the solenoid. Then it spreads out. But we'll say like all the energy is pretty much inside the magnetic field in the solenoid. And so the energy density is, the total energy over the volume. So we divide by that. And we have 1 over 2 mu naught. And then this part here, mu naught squared n squared I squared, that is b squared. So the energy density in the magnetic field is b squared over 2 mu naught. And that is for magnetic fields. When we talked about capacitors, we had the energy density in a capacitor. That'd be we interpreted that as the energy stored in the electric field. That's 1/2 epsilon naught E squared. So both electric and magnetic fields store energy. And we can, we have expressions for both of them. In both cases, the energy density is proportional to the field squared. Now, we're not going to do too much with that in this class, but I definitely wanted to go over both of these because if you take the next class in the sequence, you're going to talk about light, which is an electromagnetic wave. So light consists of alternating electric and magnetic fields. And one of the things that's most important about light is they carry energy. That's where we get almost all of our energy. Ultimately, it comes from the sun. Almost all of it, geothermal energy comes from the earth because the earth is very hot, the interior is. So we can kind of get some energy out of that, but almost all of it comes ultimately from the sun. And so like the amount of energy contained in light, well, you need to know the energy density of electric and magnetic fields. And so, we have expressions for both of those. All right. What if there's a problem? Let me just see if I can find a problem about this real quickly. Let's see. Here's one about a solenoid. Yeah, let's just do that and call this topic. We'll write down what we need to. I'm gonna just clear the board. Need some room here. I'll just write down whatever equations we need. I'm just gonna pick a problem here. It says calculate the energy associated with a magnetic field of a 200 turn solenoid. So we have a solenoid. With 200 turns. A current of 1.75 amps. And a magnetic flux is 3.7 times 10 to the minus 4 Tesla meters squared in each turn. So we're given the flux through like a single coil. So we're not really given the magnetic field, but we have the flux. We're not given the area. So yeah, this isn't going to be one of those we can just readily plug in a formula. So or maybe we can, the energy ½ Li squared. So we can, let's start with this. So the energy in the magnetic field is ½ Li squared. Let me just kind of interchange these. So let's plug in the value, for a solenoid, where here we've got the inductance, but let's replace lowercase n with capital N over L. So this is the turn density, number of turns per length, but we know the total number of turns. So let's get rid of that lowercase n. So L is mu naught n squared A L over L squared times I squared. We can get one of these to cancel out. All right, so let's see what we can do with this. Yeah, we don't know A or L. We're also going to have to look at the magnetic field. Lowercase l. So this might work out then. So again, the magnetic field, mu naught, lowercase ni. We replace that lowercase n. That's a turns ratio. That's capital N over R, or N over L. So I'm going to rewrite this. I'm going to write this as N AI over 2. So let's see, we took out an N, an A, and an I, so that leaves U naught. We have one N left over and one I left over. And on the bottom we have L. So let's just double check this. Mu naught N squared AI squared over 2L. Okay, that checks out. So what we have here is NAI over 2 times B. So I'm going to write that NI over 2 and then times AB. So we have NI over 2, then we have an A here, and this whole thing is B, and this is the flux through a single coil. So NI phi 1 over 2. And now it's a matter of plugging things in. So then we might have to play around with the units, but let's give it a go. So we have 200 turns. I'm going to do N over 2. We have 100. Current is 1.75 amps. And then phi 1 is 3.7 Tesla meters squared. We have that 10 to the 4th power on the bottom. Okay. Now, of course, like usual, the hard part is getting the units to work out. Let's see what we can do here. Well, we want to get rid of Teslas. So a Coulomb times a meter times a Tesla is a Newton times a second. An amp times a second is a Coulomb. And this might work. A joule is a Newton times a meter. So let's just check out the units. let's say we have amp times Tesla. So amp Tesla meters squared, Newton second, coulombs and joules. On the bottom, coulomb meter Tesla, amp seconds, newtons and meters. So this checks out. We do get energy in joules. So here we have let me just double check that. Here, 100 times 1.75, that's 175 times 3.7, and then divided by 10 to the fourth. So let's do that. So this is 0.65 joules. Okay. So any questions on the energy stored in a magnetic field? It's actually a very important topic because, big reason why is because of light, which has consists of electric and magnetic fields, and so it does store energy. But any questions on this one? Okay, so thinking instead of going on to the next topic, don't mind if we just stopped it a little early today, and I'll just there's kind of three more topics. We have mutual induction, and let's see, mutual induction, the LC circuit, and RLC circuit. So I'm thinking is I could record those tomorrow. Won't take that long to record those videos. I'm pretty sure I can get that done tomorrow and post them. And then we'll spend like maybe an hour on Monday, just do a few problems on each of those topics. And also over the weekend, record a few videos for the last chapter, which is RLC circuits. So I don't know, are there any questions about anything? Okay, so let's kind of stop a little early today. It's been a long day. I haven't really eaten much, and I'll record a few videos tomorrow and watch them on the weekend. So, any questions on anything? All right, so I'm going to stop recording. So yeah.